Welcome to GenAI Level Up, the podcast where we decode the future of artificial intelligence one breakthrough at a time.
Whether you're just starting your AI journey or you're a seasoned expert, you've come to the right place. Our mission is to make the complex world of generative AI accessible to everyone, everywhere.
In each episode, we dive deep into the foundational concepts, the latest research, and the transformative applications that are shaping our world. It's time to get smarter, faster. Let's level up together.
We've all seen how large language models have just exploded, right? They've gone from fancy autocomplete to these systems doing, well, really sophisticated general reasoning.
Absolutely. Passing exams, writing code, analyzing data. It's impressive.
But then you ask them to do something like execute a reliable multi-step plan in a really structured setting.
Yeah.
What the sources call symbolic planning. And suddenly...
And tools kind of fall off, yeah.
Yeah. Look, LLMs are amazing with unstructured stuff, text, images, but you give them a world with strict, formal, verifiable rules. That precision, that's where they often stumble. It's a different kind of thinking.
And the source is really zeroed in on this using PDDL, the Planning Domain Definition Language. It's like the standard for defining these structured planning worlds. Why is PDDL such a tough test for LLMs?
Well, planning itself is inherently hard. It's not just many steps. It's computationally very expensive. It's in a complexity class called PS-based complete.
PS-based complete. Okay, what does that mean for, us non-complexity theorists? It basically means verifying if a plan even works, or just storing the steps can require resources like memory that grow exponentially as the problem gets bigger. It gets hard, fast.
Wow.
And baseline LLMs. They're trained on patterns in language. They're not really built for that kind of rigorous step-by-step logical check that scales exponentially.
Yeah.
They might generate text that looks like a plan.
But it falls apart logically.
Exactly. Syntactically okay, but semantically, logically incoherent.
So these incredibly smart models are unreliable for tasks needing guaranteed, verifiable steps. Which brings us to our mission today. This deep dive into the PDDL-INSTRUCT framework.
Right.
We're going to unpack how this novel instruction tuning method teaches LLMs a specific kind of logical reasoning chain of thought to try and bridge this gap, moving from general smarts to reliable action.
Yeah, it's about making them dependable planners.
Okay, so let's get into the weeds a bit. Symbolic planning. To really get why PDDL-INSTRUCT is needed, what exactly is the LLM trying to solve here? What are the basic ingredients of one of these planning problems?
Think of it like a very formal, very strict board game setup. The problem is defined as a tuple. It's got 4 parts, Langle PA0G Wrangle.
Yep.
So Thomas is the set of fluents. These are just all the possible facts about the world. Things like block A is on the table, or the robot's arm is empty. Siraval is the current state, described by which fluents are true right now.
Got it. Facts about the world.
Then Adale is the set of actions you're allowed to take, the legal moves. Sirawaller is the initial state, where everything starts, and $, is the goal condition, the state you want to end up in.
Right, so the goal is to find a sequence of those actions, those moves, that gets you correctly from $0 to $.
Precisely, a verified sequence. And the trick, the real difficulty, is in the actions themselves. Each action, let's call it NML, has very specific rules.
Rules? Like what?
Well, first, it's precondition, often written text. This is what must be true in the current state before you can even perform the action.
Okay. You can't pick up a block if your hand is already full.
Exactly that kind of logic. And then the action has effects. These define how the state changes after the action. There are add effects, new facts that become true, and delete effects that are no longer true.
And the sources really hammer this point. This is where standard LLMs often fail, right?
Yeah.
Especially as the plan gets longer.
Yes. 10, 15 steps in, the model might lose track of the cumulative changes. It might try an action assuming a precondition holds when it actually doesn't anymore because of an earlier step.
It hallucinates preconditions, as they say.
It's less about pure memory, I think, and more about a failure of consistent, rigorous verification. An LLM might know the PDDL format, but it struggles to systematically check at every single step. 1, is the precondition met in the current dynamically changing state? 2, are the add and delete effects applied correctly to get the next state? 3, are any overall rules, invariants, still holding true?
It's that constant logical bookkeeping that's missing.
Exactly. And PDDL-INSTRUCT aims to fix that by forcing the model to explicitly show its work, to articulate and verify those logical links.
Which brings us straight to the core idea. Chain of thought? CoT Instruction Tuning. Now, I remember some earlier work suggested CoT wasn't great for planning, that it could lead to sort of rambling narratives instead of logic.
That's a fair point, and it's where PDDL-INSTRUCT is quite innovative. They didn't just ask for any chain of thought, they formalized it.
Formalized it how?
They define the CoT specifically as the planning verification process itself. It's not a story about planning, it's structured as a sequence of decomposable reasoning steps. The CoT becomes an explicit trace of the logical checks.
So it's not just, I think I should move the block. It's checking precondition, block A is clear.
Right.
True. Checking precondition, robot arm is empty. True. Executing action, pick up block A. Applying effect, block A is held. Applying effect, robot arm is not empty. That level of detail.
Precisely. It's like an audit trail. The chain of thought, which they call ZX, is a sequence of states, Z2, 1, Z2.zk, and each transition has to be logically sound according to the PDDL rules. It's much stricter.
Okay, that makes sense. And this is implemented in two main training phases.
Yes, two phases. Phase 1 is an initial instruction tuning, and Phase 2 is where the core CoT tuning with external feedback happens.
Let's talk about phase 1 first, the initial tuning. It sounds like it's about teaching the model failure almost.
That's a great way to put it. It establishes a foundation of logical critique. The model isn't just fed correct plans. Crucially, it's also shown lots of incorrect plans.
Deliberately wrong ones.
Yes, and then the task for the LLM is to explain precisely why the plan is wrong, referencing the PDDL rules, like Action 3 fails because precondition X wasn't met in state 2, or goal G is not satisfied because fluent Y is missing in the final state.
So it's learning to debug based on formal logic.
Exactly. It forces the model to connect actions to preconditions and effects in a causal way, moving beyond just mimicking plan structures it's seen.
Fascinating. Okay, then phase 2 builds on that. This is the main PDDL-INSTRUCT loop with the external checker.
Right. So the model, now tuned in phase 1, starts generating plans step by step. It proposes a sequence like start in state dollars, apply action A dollars, resulting in state SNOT dollars.
And instead of just trusting the model's internal logic,
They pass that proposed step, that Langle S-LOR A1 S1 wrangle transition, to an external verification module. Specifically, they use VAL, which is like the gold standard PDDL validator tool.
so VAL acts as the objective judge.
Correct. VAL checks if action AL$ was actually valid in state dollars, according to the strict PDL rules, and if stat$ is the correct resulting state. It provides ground truth feedback. This keeps the LLM's reasoning anchored in logical reality.
And the type of feedback VAL provides turned out to be really important. They compared two kinds.
Yes, this was a key experimental question. They tested binary feedback, which is super simple. VAL just says, yep, that step was valid, or nope, invalid.
Just thumbs up, thumbs down.
Pretty much. But then they also developed and tested detailed feedback. This is much richer. If a step is invalid, VAL doesn't just say no, it explains why.
Like what specifically went wrong?
Exactly. It might say action $1 is invalid because precondition P was false in state dollars, or the resulting state $$ is incorrect because effect E was not applied properly.
Okay, that sounds way more useful for learning. Like a teacher pointing out the exact mistake in your math homework.
Spot on. The hypothesis was that this detailed diagnostic feedback would allow the model to learn the logical rules much more effectively, to pinpoint its own reasoning errors.
And this feeds into a fairly sophisticated two-stage optimization process in phase 2 as well, right? Why split that?
Good question. It's about balancing two goals. Stage 1 is called reasoning chain optimization. Here, the focus is purely on the quality of the logical steps. The model gets penalized heavily for proposing invalid steps, like trying an action whose preconditions aren't met, even if the final plan somehow stumbles into reaching the goal.
So correctness at each step matters most initially.
Right. Get the logical process right first. Then, stage 2 is end-task performance optimization. This makes sure that the improved logical reasoning actually translates into generating complete, valid plans that successfully reach the goal G. You need both. Good logical steps and a successful final outcome.
And we should probably clarify, the goal here was satisficing plans, right? Meaning just find any valid plan that works.
Correct. Not necessarily the shortest or most efficient plan, which is optimal planning. That's a harder problem, something they flagged as future work. Getting a reliably valid plan from an LLM was the main challenge here.
Okay, so the framework is set up. The model's been trained with this detailed feedback loop. Let's talk results. What actually happened? Did it work, especially with a model like LLaMA 3?
Did it work? Oh, yeah. The results are pretty dramatic. It fundamentally changes the game for LLM planning reliability.
How dramatic? Take the LLaMA 3.8b model. With detailed feedback and iterating the training, they reach plan validity rates, meaning the plan actually works, according to VAL, of up to 94% on the classic blocks world planning domain. 94%, that's huge. What were the baselines like?
Often terrible. The PDDL-INSTRUCT framework delivered an average absolute improvement of 66% over the baseline models. Think about that, from mostly failing to almost always succeeding.
Wow, a 66% absolute jump. That's not just tuning, that's enabling a new capability.
Absolutely. It confirms that explicitly teaching and verifying the logical steps is the key.
And did the results back up the idea that detailed feedback is better than just binary yes-no?
Unequivocally, that was the second key finding. Across all the different planning domains they tested, detailed feedback consistently led to better performance than binary feedback.
By how much?
For LLaMA 3, using detailed feedback often boosted the final plan accuracy by somewhere between 5 and 15 percentage points compared to just using binary feedback. It really drives home that telling the model why it's wrong is crucial for it to learn robust logical verification.
Okay, so it works well, and detailed feedback helps. But does it generalize? Planning problems can look very different. They tested on 3 domains from PlanBench.
They did. Blocks world, which is the classic stacking blocks problem. Logistics, which involves moving packages between locations with trucks and planes. And then mystery blocks world.
Mystery blocks world sounds intriguing. What's different about it?
It's designed specifically to thwart simple pattern matching. All the object and predicate names are deliberately meaningless, like object G17, predicate P3.
So the LLM can't rely on the names truck or block to guess what to do. It has to use the pure PDDL logic.
Exactly. It forces reliance on the underlying formal structure defined by the preconditions and effects.
And how did the models do there? I imagine the baseline was pretty bad.
Abysmal. LLaMA 3's baseline accuracy on mystery blocks world was just 1%, basically useless.
1%, okay.
But after training with PDDL-INSTRUCT using detailed feedback, its accuracy jumped to 64%.
From 1% to 64% on the hardest, most abstract domain.
Yes. This is probably the most compelling evidence that the framework isn't just memorizing solutions for specific domains. It's actually teaching the model a more general capability for explicit logical reasoning that transfers even when the familiar semantic clues are stripped away.
That really feels like a significant step, doesn't it? Bridging that gap between neural approaches like LLMs and the traditional symbolic AI planning. What do you see as the bigger picture implications here?
I think they're potentially enormous, especially anywhere reliability is paramount. Think autonomous systems, self-driving cars, yes, but also logistics robots, maybe even systems used in scientific discovery or healthcare coordination.
Places where a logically flawed plan could have serious consequences.
Precisely. And beyond just reliability, this approach pushes towards more interpretable AI. Because the CoT is essentially the logical justification, you don't just get an answer, you get the step-by-step reasoning based on the formal rules. That's huge for trust and debugging.
Makes sense. Were there limitations noted in the research, things this framework doesn't tackle yet?
Oh, sure. It's still early days in some respects. The current work mostly focused on simpler PDDL features. It doesn't yet handle things like conditional effects, where an action's outcome depends on some other condition, or derivative actions, which have time spans associated with them.
Things you definitely need for complex, real-world scheduling.
Right, so scaling up to handle the full richness of PDDL and real-world complexities is a key next step.
And what about going beyond just valid plans? You mentioned optimal planning earlier.
That's the other major frontier. Can this rigorous logical verification be applied not just to find a working plan, but the best one, shortest, cheapest, fastest? That's significantly harder computationally.
And one other thing mentioned was self-verification, getting the LLM to check its own work.
Yeah, that's a really exciting long-term goal. Right now, PDDL-INSTRUCT relies heavily on that external VL validator. The dream is to train the LLM to internalize that level of logical rigor so effectively that it can reliably critique and correct its own reasoning chains, reducing the need for the external checker. That would make the whole system much more self-contained and potentially faster.
So wrapping this up, it feels like the big takeaway from this deep dive is that PDDL-INSTRUCT shows a clear path forward. By using these externally validated, structured, logical chains of thought, you can outright transform LLMs from these amazing, but sometimes unreliable general reasoners into highly dependable, structured planners. That 66% absolute jump in validity really speaks volumes.
It absolutely does. It highlights that as we ask AI to do more complex tasks, especially interacting with the physical world or critical systems, explicitly teaching and verifying logical reasoning isn't just a nice to have, it's fundamental for reliability and trust.
Definitely. So we've seen how teaching this kind of explicit logical verification dramatically improved finding satisficing plans, just getting the job done reliably. It leaves you wondering, though, if this same level of logical rigor can eventually be applied by LLMs to find truly optimal plans in these incredibly complex PS-based environments. What new capabilities, what level of sophisticated automation might that unlock? Something for you to think about as we watch these systems become potentially much more reliably intelligent.
And that brings us to the end of another deep dive into the world of generative AI.
Thank you for tuning in to GenAI Level Up. If you found this episode valuable, please consider subscribing and leaving a review on your favorite podcast platform. It helps us reach more curious minds like yours.
Join us next time as we continue to explore the cutting edge of artificial intelligence. Until then, keep learning, stay curious, and continue to level up.